So, hello everyone. Welcome to the third seminar of our webinar variance analysis and optimization. The speaker today is Professor Marco López from University of Alicante. So his talk is about optimality conditions in convex semi-infinite problem. So please, it's your space.
Okay, thank you very much.
And sorry, Hua wanted also to mention that the seminar is recorded.
Yeah, the seminar
any
is
objections, tell us right now.
Oh, sorry, I already recorded, so no way back.
Right. No, okay, perfect. And I know some friends who told me that they cannot connect because it's, for instance, in Chile, it's 3 o'clock in the morning, no? And so it's too early. And so I think it's a good idea to record. Okay, no objection from my side. It's okay? So can I start? Well, thanks, Hoa, for your presentation and all the organizers of these seminars for inviting me. It's a pleasure to stay again in Australia. Just maintaining the social distance between us. And I hope that soon in time we can recover the old normality and celebrate usual workshops, meeting people, and just taking the opportunity to interchange ideas, which is much more difficult online. Okay. This talk today is a kind of, how do you say, crash course lecture on applications, quite elementary convex analysis in the field of convex optimization, with the main objective of deriving optimality conditions for one optimization problem, which is convex, but with the particularity that the number of constraints is infinite. It's our standard issue subject along the years. And the approach is based on the subdifferential of the supremum function, subject in which we are also interested with some colleagues in Chile and many other places. Okay, this is the problem. I want to minimize a convex function, g of x, subject to infinitely many convex inequalities indexed by the small t's belonging to the x set, which is denoted by capital T, together some abstract constraint expressing this term. X should belong to this closed, non-empty, of course, closed convex set in a separate, in a Hausdorff locally convex vector space in general. The index set in principle is arbitrary. I will provide conditions in which I have to be more precise and providing certain structure to capital T. And the functions are defined in this locally convex space. And let me say that all the functions, I can generalize, extend a little bit and make the thing more complicated, introducing some technicalities. But in order to be shorter, I'm assuming that all the functions involving the problem, G and Ft, are proper López semi-continuous convex functions defined on X. So the value plus infinity is allowed, but minus infinity is excluded. The constraint systems will be denoted by tau, the set of constraints, explicit constraints, together the abstract constraint. And we are assuming all the time that the system is consistent. In other words, the set of feasible solutions is non-empty. The set of feasible solutions is represented by capital F. F is the first letter, initial letter of feasible. Okay? There is an important particular case, which many times is a kind of good example, but there are differences in the results between the linear case and the general convex case. The linear case is the simplest one. I'm assuming that the set of inequalities are affine and continuous, and so that means that the set of constraints is this one, where AT star belongs to the topological dual of my space. And there is no abstract constraint. C is the whole space, no abstract constraint. In the more particular case in which, of course, capital T is infinite, the objective function is linear, and the underlying space is the Euclidean one, we say that our problem is a linear semi-infinite optimization problem, LSIP in brief. Okay, these are our aims. We want to study certain properties of systems which serve or which play the role of constraint qualifications when I try to derive optimality conditions for problem P. Are well known. So the first part is a little bit older than the rest of the talk. These properties were introduced several years ago, but in my opinion are still important because they mean a kind of intermediate position between the most general case in the linear or the finite linear optimization problem, in which everything is polyhedral, all the properties are present, and all the things are extremely easy. These properties are the Farkas-Minkowski property, and the second one, weaker, local Farkas-Minkowski property. But the main objective, as I said before, is just to establish optimality conditions, but appealing to the properties of the supremum function. So the first task will be replace infinitely many constraints, including the abstract one, by only one constraint, and converting my problem in one convex unconstrained problem. But I need to calculate the subdifferential. And the subdifferential will be the subdifferential of an infinite, the supremum of an infinite family of convex functions. Okay, and finally, it's to formulate in the last part of the talk some weaker constraint qualifications and derive the associated optimality conditions. This is the summary. First idea is very elementary about how to transform my problem in an unconstrained one. Some drops on notation and refreshing some basic tools of convex analysis. Here there will be 4 sets of optimality conditions under different assumptions. The first one, the roundest, which is the easiest, when the system enjoys the property of being Farkas-Minkowski. The second one, when the property is relaxed to locally Farkas-Minkowski. The third one, when I remove these conditions, I have to pay a price. And the price is that I cannot obtain reasonable, precise optimality conditions, exact, precise optimality conditions. I need to derive, or what I can do instead is obtaining a kind of asymptotic, in terms of limits, optimality conditions. Not precise, of the type KKT, is what I call asymptotic optimality conditions. After that, there will be some refreshment, remembering some properties which are used in our approach. And finally, I will talk about the last set of optimality conditions under compacity and upper continuity. Compacity, not of the whole set of indices, some part of it, and upper continuity. Okay, if I remove LFM or FM property, Farkas and local Farkas, I want precise optimality conditions at the same time. I need to introduce some assumptions. In mathematics, always happens the same. If I lose, if I neglect, or I forget, or I remove assumptions, I obtain weaker conditions, weaker results. Not so interesting. And so the assumptions must be present somewhere, perhaps in the set of constraints, in the index set, etc., or in the system of constraints. Finally, I will conclude with some bibliographical comments and references. Okay, this idea is very elementary. Suppose that x bar is a feasible point and introduce this function here. Phi of x is the supremum of the objective function minus this value, the value of g at x bar. Of course, x belongs to the effective domain of g, and so this is a real number. These are the functions present in the constraints, and this is the indicator function. And so, if I consider the unconstrained problem, minimize phi on the whole space, it's obvious that this function is convex, and this is an unconstrained convex optimization problem. It's very elementary to see that if x is feasible, another feasible point, because x bar is optimal, if I suppose the x bar is optimal, I have this relation here. Now I'm supposing the x bar is optimal. And so, thanks to the fact that in any feasible point, all the functions ft take the value less than or equal to 0, and the indicator function 0, that means that if x bar is optimal for my problem, is optimal for the unconstrained problem. And so 0 should belong, is the Fermat rule, to the subdifferential of this function. But I need formulas for expressing in a reasonable way the subdifferential of this supremum. Okay, and so we use certain existing formulas, just involving approximate or exact subdifferentials of g's and ft's to solve this problem, or just to get optimality conditions of the type KKT type, just exploiting this condition here. There is another characterization which is even easiest, is this one. X bar is optimal for P if and only if X bar is optimal for this other problem here, to minimize this convex function, because f is closed and convex as far the functions ft are convex, and the set C, the abstract constraint set, is also closed and convex. This is an unconstrained problem. This is equivalent to the original one, but if I use the subdifferential, I need to decompose, to use a kind of Moreau-Rockefeller formulas in order to get something which be conceptual useful, at least from the conceptual, useful from the conceptual point of view, I want to say. Okay, notation is standard. X star is the topological dual space. Both spaces are paired in duality in the usual way. This is the Minkowski sum. And in order to make certain formulas valid when one of the summands are the empty set, I adopt this rule here. When one of the two sets is empty, the sum is empty. This is the way to represent the convex hull. Just pay attention to this, because cone of A is the convex cone, not just the cone. The convex cone generated by the set A. And also I need to assume that the convex cone generated by the empty set collapses to the origin of the space. And this is the affine hull. This is the interior of the set A, and the topology of the space. This is the way in which I can represent indistinctly, just depends. Sometimes it's more comfortable to use this notation, other times I will use this one. This denotes indistinctly the closure of A. By the way, if I don't make an observation in the contrary sense, the topology considered in the dual space is the weak star topology. The weak star topology, when this set is in the dual space, you see the symbol is the closure with respect to the weak star topology. And the ring of A is the topological relative interior, which the definition is the standard, just in the book of Salinescu and other. This is the way to represent, as usual, the normal cone at the point X to the set A. This is even more standard. I'm considering functions defined in X with real extended values. Domain of H and epigraph are represented in this way. H is proper if the domain is non-empty. Forget this condition, because now the value minus infinity is excluded. And with the copy and paste happens these things. The function is convex if the epigraph is convex, and this is the way to represent the family of the space of proper, lower, semi-continuous, and convex functions, gamma naught or gamma of X. This is a particular function, is the closed convex hull of one function, which is defined in the standard way, is such a function whose epigraph is the closed convex hull of the epigraph of the original function. This is the epsilon subdifferential. Many times I will use the exact subdifferential. That means epsilon is equal to 0. When epsilon is equal to 0, 0 is not put here. It's just without any epsilon. When you see this symbol followed by h of x, is the standard subdifferential, Funct subdifferential. And we know that for any function, the differential is non-empty, the value of one function and its closure, also the closure convex hull of this function concise, and for every positive epsilon, the subdifferential concise for these two functions, also for the closed convex hull of H. And this is the Funct conjugate. I have colleagues in France, and some of them will prefer to use the term legend Funct conjugate. This is the definition. This is a well-known property. And this is a very also well-known relation which is used several times. No? One point is a subgradient of the subdifferential if and only if this equality holds. This is one way to relate subgradients with values of the conjugate. This is the super function, the indicator function. We know the support is sublinear. I have this relation, and consequently, the epigraph of the super function is always a closed convex cone. Okay. And the last concerning these concepts, this is we are moving to arbitrary family of functions, in principle, not necessarily convex. Okay, no, I don't want to. And it's very well known that the conjugate of the infimum of this arbitrary family coincides with the supremum of the conjugates. But if these functions are in the family gamma naught, they are closed and proper. And additionally, the supremum is proper, because it could happen, the supremum could be constantly plus infinity. I have very nice relation between the conjugate of the supremum and the closed convex hull of the infimum of this function. This is a function which in principle is not convex. If I convexify it and I take the closure, is the way in which I can characterize the conjugate of the supremum. This is also well known, just confining myself a couple of functions in the space whose effective domains overlap. It is well known that the conjugate of the infimal convolution is the sum. Meanwhile, the conjugate of the sum is the closure of this infimal convolution. And this gives rise to this relation I'm using some proof, because I will give, this is a kind of class of convex analysis. I will provide some sketches of the proof. The epigraph of the conjugate of the sum is this closure, and the epigraph of the conjugate of the supremum is the closed convex hull of the union of the epigraphs. Both expressions are useful and in fact are used in our arguments. But when one of the functions f is continuous in the effective domain of the other, then I can just erase, I can forget the closure here, because this sum is already closed. We can start closed. When one function is continuous, this is a typical condition used in the Rockefeller formula, etc. And in a series of papers with Rafael Correa and Hantoute, we try to weaken this condition. But today, my intention is to be quite elementary, because here in Spain we are already in summer. Okay. Let me introduce one concept which is key in our analysis. Is the so-called characteristic cone associated to my system of constraints tau. This is the convex cone generated by the union of all the epigraphs, not of the conjugate functions. Here is the conjugate function of the indicator, of course. And thanks to the fact that this epigraph is already a cone, a closed cone, this cone is equivalent to this other one. This formula is a little bit, how do you say, involved, but okay, has a meaning, and depends only on the elements of my problem. The elements of my problem are the functions ft and the set c, and theoretically can compute the conjugates, and in the linear case, the things are easier, okay? if the constraints are affine, continuous affine. In this case, the epigraph of the conjugate is this half line, starting at this point and going upwards. And when the underlying space is the whole space, the epigraph is just at this half line starting in the origin. And so the characteristic cone is the convex cone generated by these vectors. The vectors of coefficients. Coefficients when I'm in the linear semi-infinite model, because there are elements of the dual. In any case, this cone, this convex cone, lives here in this space, in this product space. Okay, this lemma is key, is crucial for proving the generalized Farkas lemma. Again, remember that F is the feasible set, and also remember that we are assuming that this set is non-empty. We have at least one feasible solution. Then the epigraph of the support function of the feasible set coincides with the closure of the characteristic cone. And so the characteristic cone, remember from the previous slide, is the convex cone. I put here bar just to mean that I'm closing this set. Let me show a sketch of the proof. Actually, it's almost the complete proof. Consider this function is a new supremum function, f of t, and the indicator, and it's absolutely obvious that x is feasible if and only if this function takes a value less than 1 to 0, but the indicator functions always take the value 0 or plus infinity, and so this is equivalent to this equality here. But we know from the previous slides that the conjugate is the conjugate of the supremum, is the closed convex hull of the infimum of the conjugates. And by means of this a nice result for when this situation is happening for a certain function, convex function H, by means of this lemma in a paper published by Kumar and Sayop in 2003. In finite dimensions, we easily extend it to infinite dimension. We can apply this lemma to our problem by means of the function H. And so the epigraph turns out to be the closure of the cone generated by the epigraph, and this is precisely the closure of K. Now, thanks to this lemma, I can prove very easily this generalized Farkas lemma. Suppose that I'm handling two functions in gamma node, and the function phi minorizes psi over the set, feasible set F. Then this inequality happens if and only if the epigraph of the first function is included in the closure of the epigraph of this sum. This is the whole proof. Okay, this relationship here is equivalent to this one. Just the function phi minorizes psi plus the indicator on the whole space. But this is equivalent to the opposite inequality for conjugates. And this is also equivalent to the fact that the epigraph of the bigger is included in the epigraph of this one. But applying the property 7 that I put before, the epigraph of the conjugate of the sum is the closure of the sum of the epigraphs of the conjugates. But I prove in the previous lemma that this epigraph coincides with the closure of the characteristic cone. This was my previous lemma here. So I replace this by this, and it's obvious that this property is very easy to prove for any student in a first course of topology, and so I can forget this closure here, it's redundant, and I get this result. This is a kind of generalized Farkas, and you will see. We established in one recent paper other types of generalized Farkas using the same machinery, but it's the one that I'm using today. Okay, come on to this corollary. Suppose that I'm dealing with my original problem P, the infinite dimensional with infinitely many convex inequalities. I'm considering this affine, continuous affine inequalities, I'm saying that this inequality holds for every x feasible for my problem. In other words, I will say that this inequality is a continuous linear consequence of my system if and only if the vector or the product or the member of the term of the product space A star alpha belongs to the closure of K. The proof is here, just here. Is the consequence of applying the generalized Farkas lemma to these functions here. Phi is this affine function, and C is the function 0, constantly equal to 0. Then this inequality holds if and only if phi is less or equal to C over F. And so applying the result before, the epigraph of the conjugate of this function, which is this half line, is contained in the epigraph of this set plus K. But it is precisely this term here, because it is the epigraph of the function 0. But this half line is included here, and so I can add, I can forget this, and this is equivalent, I can just delete, sorry. I can delete this one because it's included in the closure of K. Remember, the K is the convex cone generated by just all the vectors in the epigraphs, and so they include the vertical direction 0, 1. Okay. The following property is crucial in getting optimality conditions for problem P. This is the property of Farkas-Minkowski. We say that my consistent system of constraints is Farkas-Minkowski if the characteristic cone is weak star closed. It seems a kind of, how do you say, technical condition without any meaning, but has a very clear meaning, providing insight to the property itself. And this is this characterization. If the system of constraints is Farkas-Minkowski, then every continuous linear consequence of the system is also a consequence of a finite subsystem. So if we consider, suppose that you are in the finite dimensional setting, okay, the feasible set is a closed convex set, and you have a half space containing the feasible set. That means that I can find a finite number of constraints such that the polyhedral associated feasible set is included in the same half space. So any continuous linear consequence of the whole system is a consequence of a finite subsystem, which is denoted, for instance, in this way. But what's even more interesting is in the linear case, the opposite also holds. The converse implication is also true. That means that if for very continuous linear consequence, there is a finite subsystem such that the inequality is also a consequence of this finite subsystem, and this happens for any consequence, the system must be Farkas-Minkowski. The proof takes 4 lines. So this is the first set of optimality conditions. This was published in a paper with Dean Gobern and Son in 2007 and provides standard optimality conditions. This is my problem. I suppose, as always, that the feasible set is non-empty. And assume that the system of constraints is Farkas-Minkowski. And this condition here, assuming that G is continuous at some point of F. This continuity seems a weak condition, but is quite strong, as I said before, and we observed several times. One mathematical aim can be just to relax, to remove this condition and replace for some weaker hypothesis. Take this point here, which is feasible and is in the effective domain of the adjective function, G, then is X bar is a global optimum, if and only if there exists, okay, this is a specific notation, But what means is there exists a finite number of positive scalars, lambda t, with associated non-empty subdifferentials, such that the origin of my space belongs to this sum here, and the complementarity conditions are satisfied. Also, this is the standard. This is the simplest KKT optimality conditions that I can get. Something's easier. Okay, if C is the whole space, this cone here collapses to 0, and so disappears in the sum. But they are very particular cases. But in general, this is the simplest formula. Oh, this is a sketch of the proof, very easy. If X bar is in the intersection of A with the effective domain, if X bar is a minimizer, this holds if a null leaf 0 belongs to the subdifferential of this sum. But here is fundamental just to decompose this subdifferential. But I can use the hypothesis of continuity and use the Monod-Rockefeller formula. And the subdifferential of the indicator function is the normal cone. And so, thanks to the fact that the system is Farkas-Minkowski, that means, remember that we have that this relationship, because that means that X star belongs, this equality here means that there exists an X star here, such that also belongs to the negative of this cone here. But if X star is in the negative, is equivalent to say this inequality holds. And so this is a consequence of the system, the constraints defined in F. But my system is assumed to be Farkas-Minkowski. And so by the characterization of linear inequalities, which are consequences of the system, this belongs to the closure, the system is Farkas-Minkowski, this cone is closed, and this cone takes this form. And so it's just to apply the fact and select some lambda t positive in such a way that this vector is expressed by means of this sum. And now I use the relationship between conjugates and subdifferentials, the formula Fenscher-Young equality, and I obtain straightforwardly the KKT1 optimality condition. Okay, the converse implication is standard. It's something technical, but without any property. The assumptions are used here. Just the continuity to decompose and the Farkas-Minkowski property just to allow me to forget the closure here. Because X star must satisfy this inequality, which is a consequence of that. A new property which is weaker, just giving rise to the second set of optimality conditions. In this way, I am denoting the set of indices which are binding at the point Z. It's very easy, easily verified, this inclusion here. This inclusion here is satisfied. Remember that if this set is empty, the convex cone, we adopted the convention of the convex cone is 0, and so this sum makes sense. This relationship is always satisfied, very easy. But what about the the converse inclusion? This is the so-called locally Farkas-Minkowski. I will say that my constraint system tau is locally Farkas-Minkowski if and only if the opposite inclusion is satisfied here. And so because always is true, when the system is locally Farkas-Minkowski, I have equality. This cone is equal to this one. Well, we say that the system is locally Farkas-Minkowski if it is locally Farkas-Minkowski at any point, any feasible point. But observe that this property is local, is established for a feasible point. Meanwhile, Farkas-Minkowski is for the whole system. So it's a weaker condition, as you will see in a while. In linear semi-infinite programming, when C is the whole space and the functions are affine, this is 0. I have very nice inclusion. But by the way, that means that if I'm in a point of the boundary of the feasible set, this normal cone is not 0. And so there must be active constraints. Because in general, in linear semi-infinite problem, even when I'm placed, located in one point of the boundary, there must not be, perhaps there are no active constraints, because I can consider a kind of parallel, tell me, how do you say, hyperplanes, just approaching this point. And so the local Farkas-Minkowski has between, among many consequences, this one. When I'm in a point of the boundary of F, there must be active constraints at this point. This property is very related to the basic constraint qualifications introduced in the book of Ruti and Maréchal and by many other authors. And they coincide or are equivalent when the supremum of the functions ft is continuous in one point of the interior. And this point, which must be in the interior of C. Okay, this is a counterpart of the other property that I established 3 or 4 slides before. Suppose that this point is feasible and my system of constraints is locally Farkas-Minkowski. And for a certain element of the dual, this is satisfied. That means that this is a supporting half space to the feasible set at the point Z. Or in other words, this is a fine continuous consequence of my system of constraints. But it is specific because it's passing to this point. So this could not happen at points in the interior, obviously. And so with such a property is satisfied, where I have a consequence of this type, defining a supporting half space, this inequality is also a consequence of a finite subsystem. Of course, of the same type. And so that means that Farkas-Minkowski implies, obviously, locally Farkas-Minkowski at any point of F. Okay? This is stronger, this is local, and implies this in any point. The second set of, is the same, by the way, no problem. Again, this is my problem, no novelty. Again, I'm assuming that the system has this property, G is continuous, the objective function at some point of F, and the system now is local Farkas-Minkowski at this point, candidate to be optimal. Then X bar is global optimum, or P is optimum, but we are in convex optimization. If again there exists a finite number of positive multiplies, just verifying these constraints. It's the same. KKT2 is the same, only difference that we are using a weaker assumption, locally Farkas-Minkowski. And the proof is easier. The proof complete is here. According to Chenizny-Rockefeller theorem, X bar is optimal for P if this subdifferential of the objective functions overlaps the opposite of the normal cone. We already mentioned this property here. And this means that if X bar is optimal, that means that 0 should belong to the sum of the normal cones by means of thanks to the continuity. And so, taking into account the property that the system is local Farkas-Minkowski, I can replace this cone, by this sum here. Because remember, this inclusion is always held. And so, for locally Farkas-Minkowski, I have equality here. And so, this is equality, and 0 must be expressed or can be expressed in this way. This is the full proof. It's the poverty of the machinery of convex analysis, which in this case is not a very tricky, not very complicated stuff. First system. Okay, I don't want to be so strong concerning the continuity of G. I'm assuming only that the effective domain of G overlaps the relative interior of F. We know that in infinite dimensions, the non-emptiness of the relative interior of a closed convex set is not for free. It's an assumption, in fact. This is non-empty and overlaps this set. If X bar is in this natural set in the intersection of the feasible set with the effective domain, will be optimal if and only if the only thing I can get is this asymptotic optimality condition. For every fixed epsilon, positive, first I fix epsilon. For every fixed epsilon, Now, for every row, there exists a number of positive multipliers, all of them associated with active constraints at the point x bar, such that I have this condition here. Observe 2 points. It's not a typo. Here is epsilon subdifferential. Meanwhile, here is exact subdifferential. And here is the unit closed ball in the dual space of radial row, because it's centered, this ball is centered in the origin. So for a fixed epsilon, for any fixed epsilon, and for every row, I have this kind of conditions. I can handle both in making epsilon smaller and smaller and also row, but this is, in this case, for every fixed epsilon of every row, this function here, or these scalars, will change. Some sketch of the proof. Okay, since I have this condition here, applying one corollary in one paper with Rafael Correa and Hantoute, we succeeded to prove this formula for the subdifferential of the sum. It's in the line of trying to get, it was our aim in a couple of papers, extensions of the Moreau-Rockefeller. But in this case, I'm not succeeded yet to decompose the disclosure here. It's just a first step. But under this assumption, the subdifferential of this sum is the intersection over all the positive epsilons of the closure of this sum. The epsilon subdifferential of G plus the normal code. No epsilon normal set, normal code. And so X bar is optimal if the origin belongs to all these sets, because it belongs to the intersection. And so, thanks to the reflexivity, I'm assuming the X is Banach, is a reflexive Banach space. This weak star closure coincides with the closure of the same convex set for the topology of the dual norm, the dual space. And so 0 must belong to the closure of this set for the norm, dual norm. That means that for every row, 0 is here. Okay? Now the rest is very similar. That means that there must be one element here, A star row, belonging to this normal hole, such that this relation holds. Sorry? This relation holds. But this vector here belongs to the normal cone. Again, this is a consequence. And my system is Farkas-Minkowski. And so I apply the property, the characteristic cone is closed, and I can replace this vector here by means of this sum. This is all. The opposite, okay, there are some transformations, but this is pure mechanics, pure algebra. Nothing conceptual. This is all. Okay, come on to the last part of the talk. We use some results which are very well known by the community. The first is the different versions of Moreau-Rockefeller. The first one is the possibility of expressing the subdifferential of the sum by means of the sum of the subdifferentials. In the first case, when the Euclidean space is X, X is the Euclidean space, is enough to assume the overlapping of the relative interiors. And when the space is general, in this case, it's enough that the function G be continuous in one point of the effective domain. In the case of Banach spaces, the continuity set of F is the interior of its domain. No? In all these cases, I have this formula, but we needed sometimes this other formula. The functions involved here don't have any requirement, convex, but here F and G are also of the family gamma node, they are López semi-continuous, and proper I have this Iriad-Ruti first formula, which cover the case in which these sets, the exact subdifferentials can be empty. They're very simple examples, beautiful, in which this formula do not apply because these sets are empty, but this formula applies. And we prove this result in this paper with Correa and Hantoute. When the effective domain of G overlaps the relative interior of the effective domain of the other function, this function is match qualified. And this function F, restricted to the affinity of the affine hull of the effective domain, this function is continuous on the relative interior of the domain. I'm confining to the affine hull of the effective domain, and f is required to be continuous there. Then I have this asymmetric formula. The subdifferential of the sum is the intersection for every epsilon. Here appears the closure of the subdifferential of f of x plus the subdifferential. This function is less required, less demanded, but the price to pay is that I cannot put here the exact subdifferential. This formula is useful for our purposes. And okay, we are going to the last KKT set, and I'm not requiring FM. I'm not requiring locally Farkas-Minkowski neither. I'm not assuming, or I'm not being so weak that confining to asymptotic KKT conditions. I don't like asymptotic because they are limits, not useful. But the price to pay, I have to put certain conditions, continuity conditions. Now I'm assuming that the functions are all the times gamma no. This is the supremum function f. And we assume the existence of epsilon node positive, such that this set of epsilon node active constraints is compact. So that means that there is a topological space, Hausdorff topological space, or at least this set is a Hausdorff topological space compact. And at the same time, all these functions defined for every z. Z is fixed, and these functions assigns to its t the value of ft at z. Z is fixed, and so is a function of t. Any of these functions is upper semicontinuous. Then we prove this result. The subdifferential of the supremum function is given by means of the intersection over this family. This is the family of all the finite dimensional subspaces passing through the point x. This is the closed convex hull, or the union for active constraints of all these subgradients. This is a complete characterization. Happens is valid in any point of the space. There are two things that I don't like. First, to have present this family here, but this is the price to pay because you know that the relative interior is non-empty when I'm in finite dimensions. When I'm in a finite dimension, in this case, the relative interior of this set is non-empty. And this allows me to do things. Okay, but the good news are, when I'm assuming that this supremum function is continuous, at some point, not the nominal point, not the point x, at some point, then I can decompose this formula and pass the normal home here. And if f is continuous at the nominal point x, or the reference point, how do you want to say, then this term disappears here. Even more, if I'm in the Euclidean space, this set, this convex hull is already closed. And so I can eliminate here the closure because it's redundant. Okay? And so let me go to the last set of KKT conditions. This is my problem. Again, I'm remembering several times in order to avoid the audience may forget the meaning of the symbols. And here I'm considering this set, which is the intersection of the effective domain of G, the effective domain of the indicator function of C, which is C, and the effective domain of the supremum of this function. Okay? And now suppose that for my point x bar, the reference point, there exists certain epsilon node such that this set, epsilon node active set of indices, the x bar, is compact. And all these functions are upper semicontinuous. Then the point is optimal if and only if I have this relationship. Here, 0n belongs to the convex hull of this expression. One detail, perhaps you don't realize that now I'm talking about semi-infinite programming. So the underlying space is Rn. This is when I can remove here closure, thanks to the property that I pointed out here. This property. And so thanks to this, I can remove closure here because otherwise I get limits of nets. And this is, okay, conceptual valid, but not very useful. In any case, observe the second thing. The second point is when I develop this condition and express zero as a linear convex combination of these terms here, perhaps the weight, the lambda assigned to the subdifferential can be zero. So that means this is a Fritz-John optimality condition. This is a Fritz-John optimality conditions. I don't like Fritz-John's optimality conditions because the role played by the objective function is absolutely superfluous. It's dummy. And so I need some kind of Slater. If I suppose that there exists one point node in this set here, such that the supremum is enough to assume that the indices are active at the point. I can forget the other constraints which are not active. If this supremum of these functions x node is less than zero, okay, I can prove that multiplier assigned to the subdifferential of G is non-empty. I can divide and I get this very nice or standard optimality conditions. Okay, this is the last set. Let me say some words. I said it's summer. I don't want that you hate me, but it's winter and it's night in Australia. But there are some progress in the direction of considering no compacity assumptions and just trying to compactify the problem. We published one paper which is close to live in a special issue of Vietnamese Journal of Mathematics, in which we consider the set T general and we compactify, starting from the trivial topology, we compactify and applying stone fetch. But that means the need of compactify, introducing new indices and new functions is quite complicated, but from the theoretical point of view, is one progress that is too much technical for today. I intended to do a kind of, I don't know, PhD class on convex analysis and to show that the proofs are quite easy. Of course, I forget or I decided not to include very algebraic arguments which are easy for any reader. No? Some references or commented references. The closedness of K was introduced by the pioneers of semi-infinite programming, were Chance, Cooper, and Kortanek in '65. In a series of papers constituted the origin of linear semi-infinite programming. And together with Miguel Goberna in 1908, in our book, we exploited this property in different contexts, even from the algorithm point of view, but especially in the duality theory for linear semi-infinite programming. The Farkas-Minkowski property for convex systems was studied by many authors, but one of the first, up to my knowledge, is Kumar, Lee, and Lee. But in the setting of Banach spaces with functions which are finite valued. They applied the term, they used the term closed cone constraint qualification instead of Farkas-Minkowski. And we prove, and also these authors prove that the Farkas-Minkowski is strictly weak to certain known interior type regularity conditions, related with conditions of the type of involving the quasi-interior, etc., in the line of the book of Radu Bot and his co-authors. The local Farkas-Minkowski property related to the basic constraint qualifications was introduced by Puente Vera de Serio. They apply to papers in economy, dealing with linear economy, and were applied to convex semi-infinite convex in one paper with Marilo Fajardo in '99, in which in which we obtained different consequences. And for a very interesting and deep analysis on these basic constraint qualifications, there was an original paper I like very much by Wu Li, Nahak, and Ivan Singer in 2000, and Ban Chong Li, this is another Li, and Kung Fun Zi in 5. And there is a comparative study in a series of papers by Li, Seng Chong Lin, Ji, and Pong in this paper. And then, concerning the references, This is the paper I mentioned. This is the papers with Rafael Correa and Hantoute. We use the results we use is from this paper and also with this one, SIOP. This is the one I mentioned about compactification of the index set. It's going to appear. This is our paper about new Farkas type constraint qualification. There are many things in the paper. Just I put the more representative results here. And this is the paper with Mariló and the book with Miguel. The paper of Jeheya Kumar, beautiful paper. A book of Uriatu-Ruti and this paper with by Uriatu-Ruti and Fritz with the formula intersecting the epsilon subdifferentials. And the papers of the Chinese friends from Hong Kong, from the Argentinian friends. Very interesting paper, giving another view of asymptotic optimality conditions. This paper by Lionel and the reference book of Zalinescu. Okay, and this is all. Thank you very much for your attention. And I will be pleased just to listen your comments and light criticism. Okay.
Thank you very much, Marco. So for your interesting talk. Is there any questions from the audience? But I have one question for Marco. So I'm really interested in the this kind of problem. So is there any future direction regarding this type of direction?
Sorry, you said future what?
Yeah, it's like potential topic. Yeah.
Okay, you can use the result because many times the people know the Valadier formula or the formula of Mitchell-Wall, but the formula of Mitchell-Wall, okay, originally was established in a normative space, but this is not a limitation because it can be extended, but they require continuity of the supremum function. I'm talking all these formulas use the tool of the subdifferential of the supremum. And so as far you get more general formula for the subdifferential of the supremum, when I say more general, I mean formulas with less assumption, with weaker assumption. In this case, you are able to derive more general results. But sometimes the price is that these formulas are quite involved. Let me, for instance, when I made my own criticism to this kind of formula, because, okay, observe that I'm handling here any possible finite dimensional subspace. But I cannot remove this if I don't introduce restrictive conditions, interiority conditions. If I consider continuity, observe. This is the Valadier formula, Mitchell-Wall formula. This is easy. So you can use this formula, but under continuity of the supremum. And this is restrictive condition. And so potential in two directions. If you like just to try to get weaker conditions in order to obtain more general formula for the subdifferential of the supremum, okay, it's a good challenge. There are things. Another possibility is to apply the more complicated formulas in different settings with less or weaker conditions to problems in which you face, that you have in front of you, and you have to solve. But okay, we're very pleased if you are interested in discussion with you about potentials. You can be more precise if we talk about it. Okay?
Yeah, and we have many questions, some questions from Enrique, John.
Yeah. Juan Enrique, yeah. Okay, so, well, first of all, I have a comment, and the comment is that it has been a very beautiful lecture, very clear, very elegant. and showing that with the most fundamental concepts of convex analysis, we can still do very and very highly non-trivial, in my opinion. So your lecture is proving the beauty of convex analysis, and that there are still many things to do in convex analysis. Well, this is my comment. Thank you for the beautiful talk. And then I have a very minor question. It's about KKT3, the third KKT theorem. Can you please show it for a moment?
This one.
Here it is. No, my question is very simple. These multipliers, lambda, rho, t, do they also depend on epsilon? I suppose so, but I'm not sure.
The notation is imprecise. They depend also from epsilon. I should choose here lambda, rho, comma, epsilon. Okay,
yeah.
If I epsilon, yes, I choose rho. These lambdas depend on rho, but also from epsilon. You are completely right. It's not precise.
Okay.
I think the advantage of presenting the proof is that you see here, no? Okay, and so I have this relationship here. I choose rho for every rho, but fixed the epsilon. And so I take here, and these scalars depend on rho, but also depend from the fixed epsilon, which can be fixed before. Okay? Completely right. Correct.
Okay, no, I was guessing that there was dependence on epsilon, but I wanted to make sure. I think it would be better to make this dependence explicit by an extra superindex. Okay, that's all. Thank you very much, Marco.
May I add on the same question? While this slide is on the screen, can you scroll back to the previous one with this KKT3?
Alex, sorry, there were some earlier questions in the chat. We have the rule.
Just while the slide is on the screen, to save time, sorry, and to extend what Juan Enrique just said, I'm wondering if there is any advantage of having epsilon and rho separately in this theorem. I have a feeling that it's sufficient to take rho equal epsilon and solve immediately the issue which Juan Enrique has just mentioned. That's it.
Okay. Of course, because this is true for every rho, in particular.
Yeah, of course, it is a consequence. You can take rho equal epsilon, but I'm saying that these statements are actually equivalent. There is, I don't see advantage of having rho at all.
No, okay. In this case, when I put here the converse implication, this is straightforward because use standard arguments. It's true, but it's not trivial. And so this is an equivalence. If I put here rho, I replace rho by epsilon, one implication is true, the other not. Okay, you see?
So you think that you cannot drop rho?
Yes. For the characterization, for if and only if, or at least for the converse implication. But I have to check.
Just looking at the statement of the theorem, I think it is equivalent with rho or without rho. But okay.
Okay.
Next, please.
Give some thought to this. I will give some thought. Okay. Thanks, Alex. Please.
So Oliver has a question. So should I read it or you directly ask?
Yes. Hi, Marco. Thanks very much for the nice talk. My question is on KKT4, where you claim that optimality is characterized by the Fritz-John condition, which confuses me a little. So usually the Fritz-John condition is not sufficient for optimality, right? So I don't see what your additional assumption is here, which makes that work.
No, okay, this is actually an if and only if but take into account that I have this term here, the normal cone.
So, and okay. And what assumption, do you have an assumption on the set D that this is compact or something?
Yes, the assumptions are here. This is important because otherwise I don't get here pure convex hull. I need closure. The conditions just guaranteeing that I can't forget the closure here is the compactness of this epsilon naught index set and also the upper semi-continuity.
Yes. Okay. So I'm thinking of an example like you only have one function f, so t is a singleton. The function f is identical to 0, and g is something like identity also. Then all your feasible points are Fritz-John points, but none of them is optimal. But then also this t epsilon should be compact, right? Because it's a, or isn't it?
Okay, I can't check the paper, but I think that is an if and only. At least the KKT. Okay, I will check, but not now. Just
yeah, sure. Okay, thank you.
Because this appears, but of course it's not an easy proof. I didn't include any sketch of the proof because it depends on the previous formulas on the subdifferential of the supremum and etc. No, and
yeah.
but if and only, but okay.
Okay, thanks.
Thanks to you.
Thank you. So, and we can have another comment, please.
So no, my comment is that I think I have the answer to the question made by Alex. And the answer is positive because if you impose in KKT3 just epsilon, you have just epsilon in the two places. Okay. I think you can move. For instance, you can increase then the epsilon in the epsilon subdifferential because you are enlarging the set. And on the other hand, if you keep that epsilon in the epsilon subdifferential and you increase the epsilon, which is the radius of the ball, then still you are increasing. So if it is satisfied with epsilon epsilon, it is satisfied with epsilon rho, even if they are different. I think, I'm not sure.
Yeah, I agree. This is exactly my point. Thank you, Juan Enrique, for supporting my point.
No, it's supporting. I think this is a proof, not just support.
Yeah. Of course.
Okay, thank you. That's all.
Thank you. And thank you, Marco.
The proof of the convex must be modified. I also support this. I think that is true because I can move one of the two parameters.
No need, Marco, to modify the proof. It follows from the statement.
Okay. But it should be perhaps easier or more, how do you say, straightforward statement.
Yes.
The same. Discussion about lambda rho must be changed by lambda rho epsilon.
Just lambda epsilon.
Yes, I will put epsilon.
The statement will be simpler, easier to prove.
And also will. Well, the first part is equal, and the second part, I suppose, must be not very much. Will be more equivalent, more or less equivalent. Okay.
Yes. Thank you again, Marco. Great talk. I'm envious. I want to be your student.
Okay.
Juan, back to you.
So is there any other questions or comments from the participants? So next week we will have Professor Marian Fabian's his talk is about, sorry. So next week our fall seminars is, the speaker is Marian Fabian, and the title of the talk is Can Pure Scale Map theorems can derive from Clark inverse mapping theorem. So I'm looking forward to see everyone next week for this interesting talk.
But you are going to escape.
Pardon?
But you yourself are going to escape next week.
I have an urgent meeting next week. I'm sorry for that. So Matt will be the organizer for next week's sessions.
Okay. And please, everybody, volunteer to give talks at this seminar.
Yes. Thank you very much for attending.
Thank you, everybody.
Just, to thank all the audience, and I'm very pleased to meet all of you. And as I said, I intended just to show what, in a very precise words, Juan Enrique said, just to provide two things. The convex analysis is a beautiful tool and is able to establish some results in a very easy way, straightforward way. Just I'm revising the paper about Moreau-Rockefeller Tice formulas, and the set that Oliver was asking, at least he is formulated as an if and only. So I have to check. And yes, but under these conditions here, okay, compactness. We will see, revise the proof also. Okay, thanks. Is all? Okay, goodbye. I'm watching.
Thank you very much.
Goodbye. Thank you, Marco.
Thank you, Marco.
Thank you, Marco.
Yeah, everyone.
And thank you, everybody.
Thank you.
Goodbye.
Marco.
Thanks, Marco.
Bye.
See all of
you,
you
Marco.
next week.
Thank you.
Thank you, Marco.
Bye.
Bye.
Thank you.